Hello and welcome to your favorite Shridevi Classes YouTube channel where we inculcate confidence and interest in science and engineering education. Today in our playlist class 12th physics in our subject electrostatics, we will first discuss the concept of equipotential surfaces and we'll find out equipotential surfaces for different charge configurations and we'll study characteristic and properties of these equipotential surfaces. Let's start. A charge in electrostatic field experience force, and in such force condition displacement of charge involve work done. And amount of work done in moving a unit positive charge from one position to another position in electrostatic field is called as potential difference, and elemental potential difference for elemental displacement is given by negative dot product of electric field intensity and displacement. Here this negative sign is significant as positive charge experience force in the direction of electric field, and bona fide positive work is done by external agency only when charge is moved against electric field. So this displacement is measured in the opposite direction of electric field, and here dl cos theta is this component of displacement just opposite to electric field, and since this displacement is measured opposite to direction of electric field, a negative sign is used. Now rate of change of potential with respect to displacement is minus e cos theta, and for different values of this theta, angle between opposite direction of electric field and displacement, we have different value of rate of change of potential with respect to displacement, and maximum value of rate of change of potential with respect to displacement is known as potential gradient, and it occurs when this theta is 0 or charge is moved just opposite to the direction of electric field. If this displacement is made in a direction making an angle theta equal to 90 degree from opposite direction of electric field or with the direction of electric field, then in that case cos 90 becomes 0 and amount of work done in moving charge in this electric field will be 0. So when there is no work done, there won't be any potential difference, and when change in potential is 0, the potential everywhere remains the same or constant. Now such positions where potential is the same is called equipotential surface. Let's understand properties of equipotential surface and equipotential surfaces for different charge configurations. If these are directions of electric field at different positions, and if a path is followed such that elemental displacement on that path always makes an angle 90 degree with electric field direction, then there won't be any work requirement in movement of charge along this surface, and such surface having identical potential everywhere is called as equipotential surface. So on an equipotential surface, electric field intensity or force lines are always normal to these surfaces, and at these surfaces for angle between electric field and displacement 90 degree, cos 90 is 0. So the amount of work done in moving a charge in electric field by any displacement with 90 degree angle is 0. Here this black line represents a surface of 50 volt identical potential, and on this red surface potential is everywhere 40 volt. So these two different equipotential surface never cut each other, because if they cut, then at cutting point normal to the surface represent two direction of electric field, and as per uniqueness theorem, one point at a time can't have two values of electric field intensities, since these two electric field intensities are not possible at this point. So two equipotential surface, though they are not parallel, will never cut each other. Now in electrostatics, conductor of any shape are always remains as equipotential surface. So internal electric field in a conductor body remains 0. There won't be any potential difference, and potential is everywhere the same on surface, inside or at central position. And in such conditions, since charge is a source of electric field, there is no internal electric field. There can't be any presence of internal net charge, and all charge have to remain only on the surface. And if this surface is symmetrical as given in this spherical conditions, then charge distribution will be uniform. So on conductor, internal electric field is 0. There is no potential difference. Potential is everywhere the same, and charge remains only on the outer surface. If conductor body is not symmetrical as shown by this peach shaped conductor body, then charge distribution on surface become non-uniform, and at sharp corners the amount of charge density or electric field intensity produced by that charge density would be higher, as at this A position position, and at flat surface charge density and surface electric field is smaller in magnitude at C, and for such intermediate curvature conditions electric field and surface charge density are intermediate. So here at A, electric field and surface charge density is higher, and at C position both charge density and electric field intensity are least. But there won't be any internal electric field, there won't be any electric field along surface, so movement of charge on surface or inside the conductor body is zero, so there won't be any potential difference. Potential always remain constant everywhere on this conductor surface. So at A, whether electric field and surface charge density are higher, but the potential is the same at A point and B and C points. For isolated positive charge or isolated negative charge, electric field is radial. For positive charge it is radial outward, and for negative charge it is radial inward, and in such conditions these pairs of common center are equipotential surfaces of different potentials. And since electric field is directed from high potential to low potential, so pair of inner positions nearer to charge, say at this position potential V1 is higher than potential of pair of far away position V2, so V1 is greater than V2. And similarly here in these inward electric field, potential is higher at outer sphere V2 and it is lower at inner sphere V1, so V2 is higher than V1 in these negative charge electric field. And point charge and a spherical charge behave in an identical manner, so this concept is the same. Now electric field is stronger close to charge position, so for same distance potential variation in inner positions is higher, so at this magenta displacement the potential difference is higher than similar displacement of this Shan arrow, since electric field is stronger at nearer position and weaker at far away positions. For a dipole configuration, electric force line start from positive charge and ends on negative charge, and these lines or curved surfaces normal to force lines represent equipotential surface, and this intermediate bisector line is known as Q axis, and at Q axis potential is everywhere the same and is zero. For parallel plate configuration, electric field is directed from positive charge to negative charge or from high potential to low potential, and in this electric field force lines are parallel and equidistant, and such electric field between parallel plate is called as uniform electric field. And in this uniform electric field another plate surface which is parallel to conductor surface becomes an equipotential surface, and in this case electric field is directed from high potential to low potential, so potential of this plate V1 is higher than V2. For a uniformly charged line, electric force lines or electric field intensities are radial outward, but they have a planar divergence, and coaxial cylinders with same center line as an axis becomes equipotential surface, so potential everywhere on this yellow highlight surface of cylinder is the same. Similarly, another cylinder with same center axial line is another equipotential surface, but inner cylinder got higher potential than outer cylinder. We hope you now understand the concept of equipotential surface and can draw equipotential surfaces for given charge configuration. The same concept will be utilized in construction of Gaussian surfaces for applications of Gauss's law. When you study our other learning video of electrostatics, your confidence and scoring ability will definitely improve. If you found our study material useful, do share it with your friends, and if you want more from Sridevi Classes YouTube channel, do join channel membership by description link, and after membership you can receive both study material and online classes support from Sridevi Classes. Thank you very much.